Okay, 5.4 here, we're going to look at enthalpies of a reaction. So since in the last section we just looked at enthalpy and heat, now we're going to look at how enthalpy and heat go along with our chemical reactions that we're going to deal with. So enthalpies of a reaction are just kind of what they sound like. Alright, it's the enthalpy change that accompanies a reaction. So they're also called heats of a reaction or heat of a reaction. Okay, we're looking at the flow of heat for the reaction, and we're looking at a delta H value for that particular reaction. And these delta H values are based on experimentation, different experiments to figure out what these delta H values are. So we're going to look here at an example of what exactly these enthalpies of a reaction are. So we're going to look at water. Okay, water is an easy example here. Okay, the equation tells us here, and for some reason it gets all weird whenever I have these in notebook. Okay, so I've got two H's and an O2 to give water. And it has delta H is negative 483.6 kilojoules. Well, what that means is that that amount of kilojoules are released to my surroundings. I know they are released because this right here is negative. Okay, delta H is noted at the end of a balanced equation, okay, and depends on the number of moles of reactants and products. So that's a big one. Okay, it depends on how many moles you have right there. So if I were to take and multiply this entire equation by 2 and put all the coefficients out here as twice as big, then it means my delta H then I would have to take and be twice as big. Okay, well, all of these equations are called thermochemical equations because you've got the thermochemistry behind it, which is this delta H number. Thermo is dealing pretty much with a lot of heat and energy. Okay, we're going to look at an enthalpy diagram, which is very, very similar to the energy diagram we looked at before, which are the ones here on the right. All right. So an enthalpy diagram is used to represent an enthalpy change that is associated with a reaction. In the enthalpy diagram for the combustion of H2, which is H2 and O2, remember combustion I need oxygen, has a higher enthalpy than the products, which is just water, H2O. So this reaction is exothermic with a negative value. Okay, I've got my reactants and my products. I lost heat to go to my products, therefore I'm exothermic. If I want to go the other direction and make this my reactant down here and this my product, then that would be endothermic, and I would have to gain heat to do that. So there are some guidelines when we use these thermochemical equations and these energy diagrams. Okay, and the first one is that enthalpy is extensive property. Remember what I just said a second ago. It depends on the number of moles. And an extensive property depends on mass or changes with the amount that I have. Okay? So my magnitude of H is proportional to the amount of my reactions. And like I said before, if you double a coefficient or half a coefficient, that's the same thing you have to do to the delta H. Okay, that's the first big guideline. The second one is that the sign of delta H depends on the direction of the reaction. So just like I said, okay, if you're going one direction, that is going to be the positive. If you're going the other direction, that's going to be a negative. And you have that example there on your paper. Okay, you have a CH4 and an O2. And if you're looking at the water example we did before, that's the same thing. One is going to be positive, one is going to be negative, depending on which direction you're going. So if you reverse a reaction, okay, and I always do reaction RXN, then that means you reverse the sign of enthalpy. And the last guideline is that the enthalpy change depends on the state. You have to be very careful on the states of matter. Okay, if we're looking at 2H2O and I'm looking at a gas, and I'm going to turn that into 2 waters in liquid form, that actually has an enthalpy of negative 88 kilojoules. So you've got to be very careful whether it's a liquid or whether it's a gas, because they go from one to the other. It's going to either take energy or you're going to get energy out when you do that. So be very, very careful when you look at these numbers that you know what state of matter your particular compound is in. So let's look at an example here. It says how much heat is released when I have 4.5 grams of methane gas that is burned in a constant pressure system. So a constant pressure system tells us some good things. It tells us that my delta H is really all the energy that I care about, and it's really my heat. Okay, so delta H really equals my Q, and Q is really then what we mean for heat. Okay, well, what this tells me here is that this delta H is negative 890 kilojoules. This is an exothermic reaction. And what you want to look at is how much methane am I burning? Well, I am burning 4.5 grams of methane, which is CH4. Okay, but remember, delta H depends on how much I have. Well, how much CH4 do I have in this equation? Well, I've got one of them. I have a 1 out in front here, so I have 1 mole. So if I have 1 mole of CH4, I'm going to have this much heat. So I need to know how many moles is this. So 4.5 grams divided by my moles, which is 16.05, and that's going to be 0.2804 moles of CH4. Since that's how many moles I have there, okay, I'm just going to take that times negative 890. That's how many kilojoules are in 1 mole, which means for the amount that I have then, I'm going to have negative 249.5 kilojoules. All right, let's try one more problem. Okay, because hydrogen peroxide can be decomposed to water and oxygen by the following reaction. I have my delta H. It says calculate the value of Q when I have 5 grams of hydrogen peroxide decomposing at constant pressure. So again, okay, I've got 5 grams and I want to know the heat, but I only know the heat for how many? Well, in this case, look, we've got 2. So I need to figure out then how many moles I have of this H2O2. So if I've got 5 grams of H2O2, I'm going to divide by my molar mass, which is 34.02 grams per mole. I'm going to get my mole number as 0.147 moles of H2O2. Well, I know, okay, that I'm going to multiply by how many I have in my equation. Well, I've got negative 196 kilojoules for every 2 moles. If you don't like this, then think of it as a ratio, think of it as a proportion. And that's the same thing. You can say 0.147 moles is going to be how many kilojoules? Well, for 2 moles, I have negative 196. It's the exact same thing. You're just going to end up multiplying and dividing by 2. Whichever way you like, a ratio or kind of figuring out the math without a ratio. We're going to have negative 14.4 kilojoules.